In the afternoons, we're having some talks, and we have today we had to have a cancellation, unfortunately, of Marcia Lamy, but we're going to have sort of with Tony Lelièvre's talk on HMC methods for sampling probability measures on submanifolds. And then after that, we're going to have two talks that are delivered electronically. So there are people are at NYU in New York, and they've been working on related topics. There's just a small amount of uncertainty in how those are going to be conducted. So we may have to make an on-the-fly program adaptation. Okay, so but hopefully not. First speaker is Tony Lelièvre.
Okay, so thank you very much for setting up this program. I will present works which are some of you already saw. So the basic work we did with basically the work we did with Matthias Rousset and Stoltz about HMC and submanifolds, using introducing also this idea of Miranda and Jonathan about reverse projection check. And then I will present work in progress, so a little bit like informal discussions about work in progress, about going a little bit beyond this reverse projection check. Okay, so let me start with directly with what we want to do. So we are given a submanifold of Rd, which is given as a zero-level set of the function psi from Rd to Rm. So you can think in the following: m is equal to 1. It will not harm too much. Okay, you could think of a codimension 1 manifold, submanifold. And what we will assume is that this grad C transpose grad C, this matrix J, this Lelièvre matrix, is invertible for all Q in a neighborhood of M. Okay, that will be one of the basic assumptions that we need. Psi is smooth, so we have a smooth submanifold. And then we are given a probability measure on this submanifold with respect to the Lebesgue measure on the submanifold. Okay, you take an exponential minus v here, and this is just a normalizing constant, so that you indeed have a probability measure. Okay, so the aim is to sample the measure nu, to compute average with respect to nu. Okay. So this appears in various contexts. I have in particular in mind free energy calculations. I will not spend too much time on this slide, but basically when you introduce constraint in mechanical system with noises, such measure appears. Okay. So I will drive you through 4 steps in order to understand to present the algorithms we are looking at, starting with just constraint over dump Langevin, then constraint Langevin, and then I will talk about the reverse projection tech and then more recent works. Okay, so let me start with overdump Langevin, and actually overdump Langevin without constraints. If you forget about this blue term, okay, this is just the overdump Langevin dynamics in Rd. You have here a Boolean motion which is in Rd. Okay, so you are moving following minus grad V plus noise. Okay, so this is known to sample exponential minus v. Okay, so when you make an average over time of this q of t, you will get an approximation of an average with respect to exponential minus v in Rd. Now we want to sample exponential minus v on the submanifold psi is equal to 0. Okay, so this is psi is equal to 0. So what is the basic idea of the algorithm I will present today is that you start from a point on the manifold. You do one step out following the gradient dynamics, and then you project back. Okay, and so if you look at the continuous time limit of that, it's basically this kind of dynamics where we are introducing here a Lagrange multiplier associated to the constraint psi of qt is equal to 0. Okay, and you decide to project back following the gradient of psi at the initial point. Okay, so that's why there is a gradient of psi of qt in front of the lambda t. Okay. So basically here, lambda t is a stochastic process, okay, which is such that psi of qt is equal to 0, and so d lambda t is in Rm. Okay. So So actually, this is one way to present things which will be very close to the algorithm I will use, but if you want to write it a little bit more explicitly, you can solve for the lambda t, and you end up with just this stochastic dynamic written in Stratanovich form, where it's here pi of q is just the projection onto the tangent space, okay, at point q. Okay, so you take the right-hand side of the overdump and you just project it on the tangent space. And this way you live on M. Okay, so the dynamics lives on M. And you can check that this dynamics has as an invariant measure exactly the measure I wrote before. Sorry, so this one. Okay, so it does the job. It samples the correct measure. Okay, and it's unique.
Come to the algorithm. Do you need assumptions on the bridge?
Yes, you need. So what I will not discuss a lot about this aspect. I will just say it has the right amount measure. Okay, and then to have ergodicity, you have to show that you can go from any point to some neighborhood of any other points. This is another job that you can do in general by using typically control theory, or it's a controllability problem basically. Okay, some kind of irreducibility. So here I'm just concentrating on building dynamics which has the right amount measure. Okay, and then you have to add assumptions on V to have indeed, or on the manifold if you want to have uniqueness. Okay. Okay, so that's the basic thing. But now we go to the computer, and so we discretize this thing. So this is exactly the algorithm I was talking about before. You do one state of the overdump Langevin, so Gn is just a Gaussian random vector in Rd, okay? And you project it back, so you introduce this gradient psi of Qn, and you look for the random multiplier so that you are going back to the manifold. Okay, so you are here, you go somewhere, okay? And then this is unconstrained Langevin, and then you project back following parallel, okay, following this direction to get the next point. Okay. That's the overdump Langevin dynamics, and you can check that this dynamics is indeed a consistent discretization of the one I presented before, in the sense that when the delta t goes to 0, you indeed converge to the previous dynamics. Okay, you can even make some kind of numerical analysis, in the sense you can look at the invariant measure of my discretized SDE and compare it to the invariant measure that I would like of the continuous in time dynamics. And you have typically error of the delta t, which is a classical weak order that you expect for such Euler discretization. So it's something I did with Erwan Faou, who is around, I think, these weeks. But okay, so you're not exactly something new. Okay, so then there is a question natural, which is how to get rid of the bias. Okay, and there is a classical answer to do that. Okay, which is Metropolis Hastings. Okay, but so if you are in RD, so it's not a big deal. You are at the point, you do overdump Langevin, and then you do a Metropolis Hastings using the density transition from Qn to Qn plus 1. Okay. The problem is that here, because of this projection step, the density from Qn to Qn plus 1 is not explicit. Okay. So to compute the Metropolis Hastings ratio, where there is this point density which appears, okay, it's not obvious at all how to do that. Okay. So that's, if you want, the starting point of all what follows, how to do Metropolis Hastings on manifolds. What does it mean? Okay, and how to do it effectively. And one way to understand what is going on is actually to lift the problem to phase space, so to introduce velocities or momenta. Okay, and here things will become more clear because I will be able to build a dynamics which will be reversible. Okay, so there will be no, in the Metropolis Hastings ratio, if you want, I will eliminate the P Q to Q tilde over the P Q tilde to Q. Okay, they will cancel. Okay, that's the idea. Okay, so I will go to phase space in order to be able to implement the Metropolis Hastings procedure. Okay, is it clear? Do you have a question on this? So now I go to phase space. So it means that I introduce momenta. So in all what follows, we were discussing that this morning. I take the mass is identity. Okay, but it's easy to generalize this to identity mass. Okay, and actually it may be useful numerically to introduce a mass. But let's take mass is identity, and thus you add to the potential energy V a kinetic energy, which is just p squared over 2. Okay, so momenta are velocity here, tangent is cotangent space. Okay, so I will not make always a difference between the two when I speak. Hopefully on the slide it's done correctly. So the cotangent space is a QP such that psi of q is equal to 0, so q is on the manifold, and p is in the cotangent space, which is a tangent space also here. So it's just orthogonal to the normal. Okay, that's what this means. What psi transpose of q times p is equal to 0. Okay. And now I extend my original measure to a measure on the phase space. Okay, so it means that I introduce exponential minus v of q times exponential minus p squared over 2. Okay, so it still have as a marginal in q exactly what I would like to sample. So the marginal in q is just mu. Okay, and in p it's a little bit boring. It's just a Gaussian. Okay, so I don't care about the p in terms of sampling. It's just there to help the algorithm to move, but in terms of sampling, it's not interesting. I will always do averages over q, right? What else? So I think that's okay. So now I will play the same game as before. How to sample mu? Okay. There is a natural dynamic which is called the Langevin. Okay, which is so again if I stay in Rm times Rm, Rd times Rd for the moment. Forget about the constraints here. It's what? It's Hamiltonian dynamics. You see, the derivative of the position is the velocity, and the derivative of the velocity is minus grad v. This is Hamiltonian dynamics. And I add to that two terms, a dissipation here and a fluctuation there, which depend on the parameter gamma. Okay, and whatever gamma, you can check that this dynamics has as an invariant measure exponential minus h. Okay, in Rd again times Rd. And is ergodic under some assumption on V, using typically in this case you can use Hamilton theory to show that you have some unique invariant measure on ergodicity. But again, I would like to live on the manifold, so I need to project it back to the manifold, and I use the same trick, which is I introduce a Lagrange multiplier times the gradient psi of q, and I impose that psi of qt is equal to 0. One thing to notice here, which is well known by people doing geometric numerical integration, is that there is a hidden constraint here, which is that if you fix qt on m, you impose the velocity to live in the tangent plane. Okay, so that's when you differentiate this, you have this additional constraint which appears. So you have two constraints if you want in these things. You have one on the positions and one on the momenta. And one way to because I want to discretize things, one way to see this dynamics is to see it as a composition of two elementary dynamics, if you want. One which is the Hamiltonian dynamics, okay, constraints, and one which is just this part, the stochastic part, constraint. Okay, so it's Einstein-Uhlenbeck process. Okay, it's q is not moving, just the p is changing in the tangent plane. Okay, and here there is no noise. Okay, I start from a position on the velocity and I go on the manifold following Hamiltonian dynamics. And I will build numerical methods which will be based on operator splitting, on splitting techniques using these two basic ingredients. Okay, so I need to explain to you how I discretize these two basic dynamics, and then I will compose them using typically strong splitting. So I start with the easiest, which is the one of the velocity, because it can be solved essentially exactly. Okay, so you can use the midpoint rule, okay, for example. And then the projection, the projection is just a linear projection here. Q is fixed. Okay, so it's just, again, using this the pi I introduced before, you can write explicitly what is Pn plus 1 as a function of Pn, Qn being fixed. Okay, so this will be one state of the Einstein-Uhlenbeck. Okay, so of this dynamics here, right? I call this elementary integrator psi OU delta t, OU for Einstein-Uhlenbeck, right? And again, Q is not changed, only P. Now I go to the Hamiltonian dynamics, and here people have worked a lot on that, okay, including Ben in the room. So to find equivalent of the Verlet algorithm, if you want, for homogeneous dynamics, but on a manifold. Okay, and there is an algorithm which is called Rattle, which is composed of this, which consists in doing these following steps. So you start from Qn, Pn. You first update Pn and Qn for using these two steps, okay, over a 1/2 time step, okay. And you look for the Lagrange multiplier here, so that psi of Qn plus 1 is equal to 0. Okay, so this is a first constraint problem related to the constraint on the positions, and then you evolve the velocities of the momenta following this dynamics, and here you have the constraint on the velocity which appears. So again, this part is not complicated. I mean, projecting here, finding lambda n plus 1 is not complicated. Finding lambda n plus 1/2 is, in general, solving a nonlinear problem, which is this psi of Qn plus 1 is equal to 0. Okay. I will come back to that. So this is the standard dynamics, which has very good properties in terms of simplicity, reversibility, as that I will use in the following. So one step of this will be denoted by psi delta t rattle. Okay. And so now I can combine these two ingredients to make an algorithm to integrate my original Langevin dynamics on the manifold. Okay. I do, for example, 1/2 of Ornstein-Uhlenbeck, or one step of Rattle and 1/2 of Ornstein-Uhlenbeck. Okay. And I have a consistent discretization of my original dynamics. Oh, very good. But there is still a bias. Okay. Because of delta t, which is not 0. So what did I gain? I gain because going to phase space, I will be able to use some property of psi delta t rattle that I will explain now. Okay. Psi delta t shares with the original flow, I mean the continuous time flow, a very interesting property, which is the following, which is that if you start from a point q on the velocity p on the manifold, and if you go for some time, and then you reverse momenta, and you go for the same time, you will go back to the initial condition with momentum which are just reversed. Okay? So this is also true for the discretized, the rattle dynamics. Okay? More precisely, you can show that for delta t small enough, you can show that if you, after one step of rattle, reverse momenta, so this is the involution S which is there, so I compose S with delta t rattle, you can show that psi delta t is an involution, psi delta t composed with delta t is just identity. Okay, so it consists in starting from QP, going somewhere for one step. I reverse momenta, I go back, and I reverse momenta again, I'm back to my initial point. Okay. There is an additional property which will be very useful in the following, which is that it is a symplectic map. Okay. So actually, we will not use simplicity. We use something which is a consequence of it. Okay, which is much less demanding, which is that it preserves the UV measure on the cotangent space. Okay, so these two properties, this is what we will need in the following to implement our Metropolis testing procedure. Okay. Why? Because now what I will consider as an elementary proposal is the following. So I do an Ornstein-Uhlenbeck. So I move a little bit the velocities. I go for some time with psi delta t rattle. I reverse momenta, okay? And now I will do an accept reject for this proposal, which is from a position on the velocity, apply psi delta t rattle on reverse momenta. And I know that in the Metropolis things, I don't need, I mean, this density proposition, if you want, which is just a Dirac because it's deterministic. They will cancel because you have if you go from QP to Q prime P prime, you go also from Q prime P prime to QP because of this involution property. Okay. So it means that in the Metropolis testing ratio, you just have the difference of the Hamiltonians which appears. Okay. Is it clear? Okay. So that's really because of this property that when you compose S with delta rattle, you have an involution. Okay. So I introduce this notation in the following: S composed with psi rattle is psi delta t. And this is now the, if you want, the generalized Hybrid Monte Carlo algorithm, which consists in, you see that in the middle I have changed a little bit the discretization I've shown before. So here it's just doing Ornstein-Uhlenbeck. Okay, so this preserves the measure. Okay, so this brick, if you want, preserves the measure that I want to sample. Then you have here a Metropolis asking step, which consists in, from this new velocity on position Qn, go use rattle plus momentum reversal, okay, and then accept reject with the probability which is this. Then I again reverse momenta. So this preserves the dynamics, I mean the measure by construction. Okay. Then I reverse again momenta. I will explain in 1 second why, but notice that it also preserves the measure because p square is invariant under this transformation. And then finally the one-half Lorentzian dynamics. Okay. So this is again a consistent discretization of the Langevin dynamics, but it has the property that there is no bias anymore. Okay. It exactly samples the right measure. Why I'm doing that, this momentum reversal, if I accept, this momentum reversal step, sorry, is because if I accept the proposal, remember that what did I do? I go for one-time step of rattle and reverse momenta. So if I continue, okay, I would go back, okay, which is not what we want. We want to have some discretization of the Langevin dynamics in the back. So what I do is that I do this proposal, and if it's accepted, I reverse back. Okay, so that if I accept, okay, I'm back to Langevin, if you want. Okay, and you can show that you have indeed a discretization of Langevin because in the small delta t regime, you always accept. So you are actually discretizing. Okay. One word to say that if you choose gamma in a very specific way, Pn plus 1,4, here's the new velocity in the Einstein is completely independent from Pn. So you are back to a Markov chain only in Q. So in that sense, this is the good way to understand how to implement Mala on manifolds. Okay, because here there is no memory of the velocity Pn with this choice of gamma, of the parameter gamma. Okay. It's because if I go back, if you take this guy, delta t gamma over 2 is equal to 1, you see that Pn plus 1, Pn, sorry, disappears in the equation. So you just draw a fresh new velocity according to the Gaussian. Okay. All right. So this is very nice, but it's very theoretical from various point of view. I said that I need to project back when I do rattle. Okay, so I need to solve the nonlinear problem psi of Qn plus 1 is equal to 0 at some point. Okay, and there may be no solution to that. Okay, so psi delta t may be not defined. Okay, because I cannot project if I go too far. And even if it's defined, it may be the case that after reversing momenta, when I want to go back, okay, actually it's not well defined. Or maybe I can even be able to define going back, but not going back to the initial point. Okay, so maybe I can explain that maybe I explain it directly. Let me do it on the blackboard, it would be easier. You may be in a situation where you start from a point, okay, you go for some time, so without constraints. This is the gradient of psi, so you project somewhere. So this will be my next point. So this was a Q on a P. So this is the new P if you want. You reverse it, okay, and you go back. So what you know is that by construction, because of, so if I use here the normal, you know that when you go back here, okay, there will be a Lagrange multiplier so that you go back to the initial point. I mean, it's built in the Verlet, the rattle algorithm. Okay, but it may be the case that there is another solution when you project that, which is not the initial point. Okay, so here comes into the picture the way you actually numerically solve the constraint psi of q is equal to 0. Okay, will it choose this one or this one? Okay, so that explains the difficulty that we may have in practice. Okay, and which will not make actually this one. Okay, this will not be disappears in the Metropolis async ratio. So this is where comes this idea of the reverse projection check, which have been introduced by Miranda and Jonathan. Okay, but let me explain a little bit what is going on here. So to explain that, I need to be a little bit more precise about what I call the Lagrange multiplier here. So this is just a rewriting of rattle. Okay, so I presented it before. I just rewrite it in 2 steps only. This was my Pn plus 1/2 before. Okay, and these are the two Lagrange multiplier, which is difficult to compute the lambda n plus 1/2. And here I just use the projection for P. So you see that the step which is difficult is this one. So I start from Qn with a velocity Pn. I do an unconstrained move, and then I need to project back to the manifold. So I need to find the lambda n plus 1/2 so that psi of Qn plus 1 is equal to 0. So to formalize a little bit what is going on here, I said that delta t lambda n plus 1/2 is a Lagrange multiplier function of the initial point, Qn, and the point I obtain after one step of unconstrained move. Okay, so I start from somewhere. This is my Qn. I end up somewhere else. This is my second variable here. Okay, I'm looking for the Lagrange multiplier, which will bring me back on the manifold. Okay, so I define lambda like that, and I call it the Lagrange multiplier function. So it takes 2 parameters, Q, which is on the manifold, Q tilde, which is not, and it is such that when I add to Q tilde grad psi of Q lambda Q tilde, I'm back on M. Okay? So this is just to introduce more precisely what is this Lagrange multiplier function. It is typically defined on an open set of M times Rd. Okay? We cannot project anything on the manifold. And the question is, what do we need on lambda so that everything works? Okay? And if it doesn't work, how to correct? That's the question to ask. Okay? Since lambda is only defined on a subset of M times Rd, it means that my algorithm here is only defined on a subset of Qn Pn. Okay? I cannot move from anywhere. So I call A all the points Qp such that I am indeed able to perform the Rattle dynamics. Okay? So that's my ensemble A. And psi delta t, which is the composition we remember with the momentum reversal, is also defined in A. So you can show that if lambda is C1, you have a C1 local diffeomorphism, okay, which is a good start, which preserves the phase space measure. Okay, so that's basically computing. It's a simplicity of Rattle, which is behind. Okay, it's just a computation of a Jacobian. Okay, it's something local, let's say. But now remember, in my algorithm, I want to show that psi delta t composed with psi delta t is identity. Okay, so I need to look at the composition of this guy. And what is clear is that even if I am in A, psi delta t is well defined, it's not clear that psi delta t of A is in A. Okay? So this is where I need to introduce this B, which is all the points in A, so that when I do one step of Rattle plus momentum reversal, I still in A. Okay? And I add, in addition to that, that when I compose the two, I'm back at the initial point. So everything I need so that everything works. Okay? So that this, for example, does not appear. Okay? I don't choose this point. I'm always choosing this point. Okay? So this is a set on which everything will work. So on this set, I just apply psi delta t. On the complementary, I reject. And so I stay at QP. Okay? Make sense? So that will be my modification of psi delta t, which make it really reversible numerically, not only for small delta t. I mean, this is really reversible. Okay, there is no error due to the numerical solution of the constraint here. So what you can show is that this B is well defined. It's a union of path-connected components of this set actually. So you have A, you have the inverse image of A by psi delta t. This makes an open set, and you take the connected component of this, and B is a union of path-connected component of this set. Okay, so it's a set which is open, and so you can use that to show that psi delta t rev is indeed globally well defined, preserves globally the measure, the Liouville measure, and satisfies exactly the identity. It's clear when I'm not in B because I don't move it, okay? And it's imposed in some sense with the definition of B when I'm moving. Okay, so that's my psi delta t rave, and so the way it works again is that I start from a point QP. I'm asking first am I able to perform one step of rattle or not? If not, I stay at P. If I'm able to do the rattle, I reverse momenta, and I ask, am I able to now do a rattle back from Q1 minus P1? If not, I return QP. And if I'm able to go back, I still checking if I'm indeed coming back to the initial point after momentum reversal, which is the last step check if you want. Okay. And if not, again, I'm returning Q. And if it's only if I'm passing all these three, if you want, conditions that I'm indeed moving. Okay. And this is called the reverse projection check, as introduced in this paper. So there is a question how to build this lambda concretely. Okay, so given the time, I will not go into that, but you can use Newton techniques basically, Newton theorem to implicit function theorem. Sorry, to show that implicit function theorem to show that you can do it locally, and you can show also that the Newton algorithm is doing the job when implemented. Let's say. Okay, so I will not go into the details of that, but you can build functions lambda, okay, implicit function, Lagrange multiplier functions, such that the set B is non-empty, okay, because otherwise the theorem is empty. Okay, I never moved. So this is the final algorithm if you want. I just replace psi delta t here by psi delta t rev. Okay, and now I have an algorithm which is fully implementable and which indeed admits mu, as an invariant measure. And then to prove ergodicity, you have to check the reducibility, which can be done. So I mean, it's a separated issue if you want. You have to check that for any point, you can find a velocity to go to any other point. There are many variants that you can think of. So in psi delta t rev, you don't need to use the potential V, which is actually defining the invariant measure. So you can play with the V, the potential V. You can take V is equal to 0. This is a random walk, okay, on the manifold, and you accept reject with respect to the target. Okay. Again, if you choose a gamma which is very particular, you obtain a dynamics which is Markovian in position. Okay, so like a mala. I presented everything with only one step of rattle, but you can say I use smaller time steps, okay, or I use maybe geodesic integration, okay, as Ben would probably suggest, so that it's easier to stay on the manifold, okay, so that I will increase my acceptance rate, okay, that's also things that you can do. You can actually use exactly the same kind of ideas to enforce inequality constraints, something we were discussing this morning. And again, for numerical purposes, it may be interesting to consider non-identity mass matrices, okay? I can elaborate on that with people who are interested on that. Okay, so let me now go to the final things we did recently. So it's a work of progress again. So it's not. This is not finished. This is not published. So in practice, actually, there are many situations where you are not able to compute only one solution, but many solutions to that. The typical things we have in mind is when psi is a polynomial function, so you have an algebraic submanifold, okay? And you can actually find, if not all the roots, okay, many of them, okay? If you think of just a circle, I mean, it's just a polynomial of order 2, you can find everything. And more generally, there are packages to do that on in many cases, to actually find more than one root to psi of blah blah of lambda is equal to 0. Okay? So one question we ask here is, what can we do if we have many solutions? Okay? What does it mean? It means that I don't have only one solution to this problem, I have n solutions, okay? And so I have n functions lambda I. And of course depends on the starting point, on the end point. Oh, wait, I mean on the point which is outside the manifold. Okay. So I have n of q tilde c1 functions lambda I, okay, which are such that q tilde plus grad psi lambda I is in n. Okay. What can we do with that? So again, we have two situations in mind. Either we have all of them because it can be analytically computed. Okay, this happens. Or we have many of them because it can be numerically computed. We have in particular in mind, if I use in particular Julia packages, it's called polynomial roots, and it's called homotopy continuation. These are typical techniques to solve these equations in case when psi is a polynomial function. Okay? So how can we play with that? So one idea is the following. So I have a Q on the manifold, a Q tilde outside, and I'm able to compute many solutions. So here, let's say 2, okay? I can project here or there. So I give a probability to each of these solutions. It could be the uniform probability, 1 over the number. Okay? It could be something else, because you would like to, for example, to favor moves which bring you far from your original point. Okay? So you put more probability to go to other components, for example, connected components of your manifolds, of your zero-level set. Okay? You play with that. And the idea is basically to do as before, but to choose one solution at random among the possible projections. Okay? How to adapt the algorithm I've presented before so that I have still the right invariant measure. That's the question we ask. Okay. So let me bring you through this algorithm, which is, so since you have seen the other one before, it should not be too much complicated. So the first step is exactly as before. I keep the position fixed and I just change the velocity as before. Then I compute all the ways to go back to the manifold. So to all the Lagrange multipliers lambda I. Okay, this is Q tilde n plus 1 is what I have obtained with the unconstrained step. Okay, and I choose one of them with the probability that I have assigned. So you can think of the uniform probability if you want to keep it simple. Okay. Then I apply the psi delta t, so the rattle plus momentum reversal, for this Lagrange multiplier that I have chosen. Okay, so I'm really going forward, you know, with this Lagrange multiplier that I've chosen. And then this comes the equivalent of the reverse Polish check, which is, so I went forward, reverse momenta, and now I'm going backward, and I look at all the way. Okay, I can go backward. And I'm asking a question which is it indeed the case that among the solution to go backward, I have the starting point I had from the beginning? Yes or no? Okay. If not, I just reject, this is reject, and I go to the last step. If yes, I have a Lagrange multiplier with index Gn here, which is such that I am indeed going back to my initial point. And now I'm doing the Metropolis Hastings procedure as before, except that I'm here to take into account the probability to choose the Lagrange multiplier forward, this is on the denominator, and the probability to choose the Lagrange multiplier backward, this is on the numerator. Okay? Makes sense? So that's a quite natural way to generalize, if you want, the algorithm I've presented before.
So if you make a deterministic choice, does it still work?
Yes, if you make a deterministic choice, you are back basically to the solution before, which is that you have either zero, but you can have zero solution because you are too far from the manifold, so it's impossible, or one, the one you have chosen, okay?
I'm in a deterministic choice for the pi's here, for the probability pi.
Sorry. The probability pi is deterministic here. I mean, it's not. I mean, the probability is deterministic, but you choose at random the Lagrange multiplier.
Yeah, but you could say I always take the one that is furthest away from my solution. And
so yeah, you can do that. So if you do that, you will have either 0 if it's impossible to go back, or 1 if you can go back, you choose the furthest. And then the question is it true that by taking the furthest, I am back to the original point? Yes or no?
So that works just as well.
Yeah, that's what you said. Yeah, you can do the deterministic version, of course. Yeah. A slide to say that imagine that I have to finish. No. Imagine that I am in the very good situation where I can compute all the solutions, okay, and I put uniform probability of them, okay. It simplifies a lot the algorithm because I know by construction that the rattle dynamics is such that there is among the possibilities of among the projection one which is exactly going to bring me back to the initial condition. Okay, this is just algebraic. You know, when you do rattle one step to go backward, you just have to reverse the Lagrange multipliers. Okay, the one for the position of the velocities. Okay, so if I am sure that I have all the solutions, I don't need anymore the reverse projection check. So this is why I call this beyond reverse projection check. So it gives me this algorithm where I update momenta, I compute the Lagrange multipliers, I choose one of them with uniform probability, I compute the move, and I just need to compute how many solutions I have when I go back. Okay, I just need the n and the n forward and the n backward, which is the number of Lagrange multipliers forward and backward. Okay, and in this case, I never reject, if you want, because I'm sure that among the Lagrange multipliers to go backward, there is one which is doing the job, which is indeed bringing me back to my initial condition. Okay, so that's, if you want, I'm avoiding one reason to reject my move, which is good. So again, you can adapt the argument I presented before to show that mu is an invariant measure of these dynamics. And I'm running out of time now, but just to say that we checked that on probability measure on the torus, so very simple example. Okay, I must say. Either the uniform law on the torus, so just the Liouville measure if you want, or a law which gives more probability to these sides of the torus. So a bimodal, if you want, distribution on the torus. Okay, and as you expect, it helps to actually use this kind of techniques because you favor jumps. You can favor jumps which indeed brings you back when you have to choose among many solutions. If you choose the one which brings you far from where you were originally, it will help to move a lot. Okay, and this is of course very good for MCMC. Okay, I want to move and I want to accept at the same time. So that's the numbers which are in the following slides show you. It's not biased and it helps. So this is after some time we look at what Newton is doing, so what I presented before, and what the other techniques are doing, and you see that for a given number of time steps of iteration of the algorithms, I'm much quicker to the equilibrium measure for the other techniques than for Newton. Okay, and that's this is the parametrization of the law on the torus by the two angles phi and theta. Okay, that's just with this I leave it there, and these are a few references on this subject. But again, the last part is not even on the archive yet. So thank you for your attention. Sure. I can hear you. Hi, John.
Go ahead.
Go ahead.
Okay, can you hear me?
Yes.
Okay, so thank you for the nice talk. My question, the last part where you talk about what happens if you know all the solutions to the projection equations. So I'm wondering if you can elaborate more on what kinds of examples you have in mind. And the reason I ask is that I agree that if you have a single algebraic equation as a constraint, it's fairly easy to find all the solutions for many equations. But if you have multiple algebraic equations that are degree 2 or higher, my understanding is that it can be very tricky to find all the solutions, even using packages such as the ones you referenced. So I'm curious what for which kinds of examples would this be efficient?
Yep. Thanks for the question. So honestly, for the moment, we just play with solved problems. So this comes from discussion with Paul Briding from Berlin, and it seems that in some applications in topology, they have probability measures on algebraic manifolds, and they have to play this game. So
Okay.
It seems that in this context, it makes sense to look at this problem. One thing I would like to insist on is that even if I don't have all the solutions, okay, I can still play the game I've presented. So even if what I need an algorithm which give me an ensemble of solutions, okay,
Sure.
and from that I can generalize basically the reverse projection check if you want to this situation. So
Okay, yeah,
even if it's not perfect, even if you have a solver which only gives you a few solutions, okay, use it,
Yeah.
use them. That's the basic idea. Use them, okay?
okay, as long as the solution sets intersect, I guess
Exactly.
this will still work. Yeah, okay,
Yeah.
thanks.
Okay, I should just check, is there anybody who has a question here? Okay, I suggest we thank Tony for his talk.